Hi, Math 211. I'm going to go over two strategies that came out in our number talk for 32 times 15 and connect them to visual representations. And then last, I'm going to share a strategy that did not come up during our Zoom call. That is an important one to reflect on. So 32 times 15, one strategy that emerged in our Zoom session was several students did 32 times 10 and obtained a partial product of 320, and 32 times 5 and the partial product of 160. Then they added those two partial products together to get 480 square units. The students that did this were drawing on the distributive property. They thought about 32 times 15 as 15 being decomposed to 10 plus 5, and that being equivalent to 32 times 10 plus 32 times 5. But let's connect that to a visual representation. So 32 times 15, you can think of that as a rectangle that has a side length of 32 and a side length of 15. Because of my kind of little graph paper here, I'm going to do it 15 like this, where each side of the little square represents 5, so 5, 10, 15. And then I can do 5, 10, 15, 20, 25, 30, and then a little bit past for 32. Okay, so suppose this is our 32 by 15 rectangle. If I wanted to see the partial products of 32 times 10 and 32 times 5, I need to think about taking this 32 and, taking this 15 rather, and decomposing it to the 10 and the 5. And you can see if I do that. I then have one rectangle that is a 10 tall and 32 wide. So this is a 32 by 10 or 10 by 32 rectangle. That's 320 square units. And then this slimmer rectangle is 5 by 32, 32 times 5, and that's where we get the 160 square units. All right, this is one of my personal favorite strategies that was referred to as doubling and halving. And it was referred to doubling and halving because the student in our class that did this, he did 32 divide by 2 and got 16, and then 15 times 2 and got 30. And he kept going, and so he did 16 divide by 2 and get 8, 30 times 2 and get 60, and so on and so forth. And so what we're going to explore is, why is 32 times 15 the same as 16 times 30 with a visual representation? Before we go there, I want to revisit our explanations in class. So in class, people said, well, 32, if I have 32 and get 16, that's dividing by 2, and dividing by 2 is the same as multiplying by a half. And then if I do 15 times 2 and get 30, I write it that way. People reasoned, well, multiplying by 2 and dividing by 2, people use the word opposites, and we said those are inverse operations. But if we look at it with the expression I wrote down here, you can do associative property on multiplication and rewrite this like this: 32 times 15 times the 1/2 times the 2. And what I like about rewriting it like this is then you can see that 1/2 times 2, this piece here, this is 1. And so really what you're doing is multiplying by 1. And so in class I asked, is this always true? And we came to the conclusion that doubling and having always does work. When? Always. Is there a time that it's maybe more efficient to use? Sure. Like it's nice to use when one of the numbers is even. But even if both were odd, it technically would always work. All right, so let's go to our visual representation. Again, I'll draw the 15 by 32 rectangle. then I will draw a 16 by 30 rectangle and try to describe why these are the same. Just think of these as sketches. I don't have the best grid paper on here. So let's look at our 15 by 32 rectangle. So with doubling and halving, we're essentially halving one of the side lengths and doubling the other side lengths. Let me switch to orange here. So if this is 32, and if I halved that side length, that's thinking about this as 16 and 16. The half would approximately be here. And so if you want to think about that with this visual representation, basically you want to think about this whole part that I have shaded in blue and moving that down below. And if you do that, you've halved the 32 side length and you've taken that 16 and that matches up right here. And then this length right here, this is 15 because it's a rectangle. So when you put it over here, it's also 15. And basically you make the image we have on the right, which is a 16 by 30 rectangle. But the area will have the same amount of area because I just decomposed it and put it back together. Okay, now let's talk about a strategy that I haven't talked about yet, which is sometimes when students see this, what they'll first do is they'll do 30 times 10 and get 300, and then 2 times 5 and get 10, and they'll add this up and they'll get 310, which, since our previous two answers were 480, we can assume this is an incorrect answer. But why is it incorrect? Well, if I make my rectangle again, so there's 15. And here's my 32. If I think about the 30 and the 10, where are those dimensions? Well, the 30 perhaps is here, or this is 30 and this is 2. And the 10 comes from perhaps here, this is 10, this is 5. So the 30 by 10 is right in here. I'll highlight it in green. This is the 10 by 30, or the 300 square units. And then the 2 by 5, you can see that this is 5 tall, and then you can see it's 2 wide, this little piece in here. So that's the 2 by 5, which is the 10 square units. So you can see with this, we're actually missing 2 partial products. That's what I'm highlighting in yellow. And so we need to add those in. So what are those? Well, we can see that this is this first, or this larger yellow rectangle. It's 5 tall and 30 wide, so that's 5 by 30. And then this one right here, it's 2 wide, and it looks like it's 10 tall. So we're missing a 5 by 30, which is 150, and we're missing a 2 by 10, which is 20. And if we add those missing partial products, you can see we get the same answer that we got above. But I do want to talk about why I think this incorrect answer of 310 is a really logical answer. I think it's super logical because if this was not multiplication, let's say this was addition, 32 plus 15, it would indeed make sense to do 30 plus 10 and get 40, and 2 plus 5 and get 7. So for addition, it makes sense to add our 10s, add our 1s. Just that this doesn't extend to multiplication. Why doesn't it extend to multiplication? Well, the why is because, well, essentially here, we're missing these partial products. Okay, I do want to talk about what some students will say. Sometimes when students see this, they'll notice these 4 different partial products up here, and they'll say, oh, this reminds me of my algebra days with FOIL. And so like 32 times 15, you can think of 32 as 32 is 30 plus 2, and 15 is 10 plus 5. And then FOIL, it's an acronym for first, outer, inner, last. So basically saying take the first terms, multiply them together, 30 times 10. The last terms, 2 times 5. And then the outer and the inner are these here, I think. And you get the same answer as above. But I have two comments about that. The first is FOIL is a procedure that really only works if you're multiplying two numbers together and these two numbers are then decomposed into two numbers. So basically you have a kind of binomial, if I'm using algebra words times a binomial. If you decompose it any other way, like 3 terms with 4 terms, FOIL doesn't work. It only applies to this one unique situation. The other thing with FOIL is it's just an acronym and a procedure. And I think that's one of the things we've talked a lot about in this class is unless you know why it works, like unless it comes out of something, like the procedure emerges out of the conceptual underpinnings, it can be meaningless to students. And so what I personally love about this is this representation up here is that we can see multiplication is more than repeated addition. We can see multiplication as area. That's one of the definitions of multiplication. And one of the things I think is so cool is that all these strategies, and we've only talked about 3 here today, we can connect to that same visual representation of multiplication as area. And connecting multiplication to area is also really important because I think geometry is often an underrepresented area in mathematics. And so when you're doing number and operations, it's a really natural extension to connect to area in geometry.